Discovery intelligence operates as a highly structured, long-horizon scientific system designed for complex decision-making and ongoing data discovery. As the platform grows, the primary challenge shifts from raw computation to the way a human operator interacts with deep, multi-layered structure. The system tracks canonical evidence, run states, candidate states, specific scientific claims, and precise belief updates over time. Accessing this data requires an operator to manually retrieve the correct object, inspect the exact claim, or surface the precise experiment state. Executing those actions manually across thousands of interconnected data points is practically impossible for a single human user. Operators require a natural language interface to request specific data paths while maintaining the precision of a direct query. The interaction bottleneck appears when the structural depth of the data exceeds the user's ability to navigate it. The common industry reflex involves connecting a massive, closed API language model directly to a proprietary database. Relying on a generalist AI model to manage scientific truth introduces the risk of corrupted, non-deterministic outputs. Generative AI must be restricted from determining scientific truth, rewriting canonical evidence, or assigning belief states. System integrity depends on a strictly bounded interaction membrane acting as a mediator for the underlying data. The Gemma family of open weight models provides the specific architecture required to build this membrane. Effective mediation requires an AI layer that interprets user intent without ever mutating the canonical scientific data. We can trace this logic using a specific request. Find recent runs with caution patterns similar to Claim 42. Local hosting is a prerequisite here. By using open weights, the model parameters are stored and executed directly within the system's own secure environment. Remote API calls require transmitting proprietary data to external, third-party servers. Maintaining local control ensures deployment consistency and allows for modular specialization of the model weights. Long-term scientific platforms must retain direct control over their interaction layers and data flows. The query string first reaches embedding Gemma, the initial layer of the membrane. This model variant focuses entirely on semantic translation rather than text generation. It converts text into a dense numerical vector representation. This mathematical process maps user intent into a precise coordinate space. The system retrieves relevant run summaries by identifying nearby points in that space, matching based on meaning instead of keywords. We apply this retrieval method to session summaries, candidate states, and belief updates. Embeddings provide a reliable semantic retrieval layer that finds existing data objects without hallucinating new information. The retrieved context and the user query move to the next stage, Function Gemma. Function Gemma translates natural language intent into a structured, executable action. The model parses the request and generates structured JSON, defining the exact toolname and parameters required for execution. Firm, the generative process concludes once the schema is generated. The deterministic DI core receives the JSON payload, executes the specific scientific function, and returns the factual data. Gemma is re-engaged only at the end to explain these factual results in bounded natural language. This creates a strictly mechanical routing interface into safe, deterministic scientific services. Ensuring the model stays within these routing boundaries requires specific behavioral constraints. Fine-tuning specializes the model's behavior and vocabulary without needing to inject new scientific knowledge. We compute gradients on a narrow dataset to update specific parameters within the network. Parameter-efficient fine-tuning, or PEFT, allows for this specialization using a fraction of the memory required for full model updates. We target DI-specific terminology, tool schemas, and strict response formatting. This process locks the model into its interaction role, ensuring it adheres to the system's linguistic and functional rules. In this context, fine-tuning acts as a mechanism for behavioral adaptation and routing discipline. Integration follows a phased roadmap: embeddings for retrieval, function calling for routing, and fine-tuning for vocabulary. Gemma is permitted to retrieve data, route requests, and summarize existing canonical outputs. The model is restricted from modifying scientific truth, overriding evidence, or ranking candidates. This bounded role doctrine reduces the risks associated with deploying language models in high-stakes environments. It keeps the scientific core deterministic, inspectable, and provenance-aware. Restricting the scope of the AI is the safest way to apply generative models to rigorous scientific research. The completed architecture shows a fully integrated system where intent and data remain distinct. External text queries are intercepted by the Gemma membrane, processed by the core, and translated back for the user. Functional decomposition and sound system architecture remain more important than the scale of the model itself. Discovery intelligence computes the science. Gemma provides the membrane that allows humans to interact with that computed truth.